The first talk is by Marc Joye from Zama, and it's going to be on NTRU modulo X to the N minus 1.
Hi, everyone. So FHE is a wonderful technology, so it allows anyone computing anything over encrypted data. I mean, that's very beautiful. In practice, not that easy. And one of the main issues we have with FHE is dealing with the noise. And as you know, so just for security, so we need noise in the ciphertext. But the more you play with the ciphertext, so the more the noise tends to increase. And it might be the case that at some point there is too much noise in the ciphertext and you won't be able to decrypt anymore. And so that has been known from some quite long time, and we know the solution. And so please meet Greg Gentry. And so the solution is truly beautiful. I mean, again, very easy, but truly beautiful. It's a very elegant way to solve the problem. And his idea was, wait, so we have homomorphic encryption, so it means that if you encrypt, if you are given the encryption of X, you can get the encryption of f of X. And now if you take for f the decryption algorithm, so if you give us an input, a ciphertext, and the key to evaluate the decryption, then you get as an output another ciphertext, encrypting exactly the same message. And what is nice in this idea is that because the decryption algorithm removes the noise, so it means that at the end, so you may end up with a ciphertext that is less noisy than the input ciphertext. And if it is the case, then you won. I mean, you win. So you can iterate again and again. So there is a way to evaluate over encrypted data. So as soon as there is too much noise, you just apply your bootstrapping. So let's take a look at a concrete example. So assume that we'd like to apply that ID to TFHE. Just as a recap, so the way it works. So first, you have to generate a mask, which is just a random vector. So in this case, on the torus. Mu is the message you'd like to encrypt. You first add some noise, so you get that noisy message. And then you use the secret key S, compute the inner product with A, so the mask. You add mu star, and you get the second part of the ciphertext, the body B. So that's for encryption. And then to decrypt, so just do the same, but in the other direction. So you first compute the phase, in this case, B minus the inner product of S and A. You get mu star, and then you run mu star, and you get back the value of plaintext message M. So remember that in Gentry's ID, the idea was to evaluate the decryption algorithm over encrypted data. And so in this case, so it means that you have to evaluate those two operations. So the first one, as you can see, is a linear operation. So that's fairly easy to do. So the first one is easy. What is tricky is the second one. So how can you round over encrypted data? And there is one way to do it. So you can use polynomial for doing that. And so the way it works is as follows. So you define a polynomial just like this one, so of degree n minus 1. And if you multiply that polynomial by that monomial x to the minus j, then you end up with a polynomial whose constant term is vj. I mean, that's a very basic observation, but this is very useful, as you'll see. And just using that trick, so we can round values. And here is the way it works. So assume that you are given as an input 2-digit values. So in this case, we have 30 values, and we'd like to round those values to just 1 digit. Okay? So we'll use the polynomials to do that. And so we start with that polynomial as we just saw before. And so if you multiply by x to the power of minus j, you end up with a polynomial whose constant term is vj. And so what you do, so remember that we are computing mod x to the n plus 1. So for n, we take a power of 2. So we have 30 possible values. So we take, for example, n equal to 32. And so the way to choose those coefficients here, so for example, you start with this one, so that guy, so degree 0, and so the rounded value is just 0.0. So you put that value here, then you continue with the next one, so you put 0.0, and you continue. Okay, so for example, for this one, 10, so the rounded value is 0.1, so you put 0.1 over here. So you have that polynomial, and what you have to do is just to round, you just evaluate that value, so minus 100, that's the noisy value. You multiply by that polynomial and you get the rounded value. You see? So it's quite powerful. And again, I mean, so once you know the trick, I mean, it's easy, but again, that's quite a very beautiful way to do the rounding. So that has been used in TFHE. So for example, so you see that we need polynomials. So it makes sense to look at ring version of LWE. And so if you use a ring LWE to encrypt, so it's basically the same as LWE. So you start with a random polynomial, so the mask A, then you just scale so in this case, the message is a polynomial. You scale it by some factor delta, you add some noise, you get the noisy plaintext, and then to get the body polynomial, you multiply the secret polynomial S by A, the mask, and you add the noisy message. And you get the ciphertext, which is the pair A, so the mask, and the body B. Okay? So that's the usual way, I mean, that's one way to do it. And what you have to observe here is that ciphertext is made of two polynomials. Okay? So that's the main observation. But there is another way. So, I mean, ring LWE is not the only one. So you may also use NTRU. And so this is just a reminder of the way it works. So you first choose some random noise, then you form the message, I mean, the noisy value of the message in the same way as for a ring LWE. So you scale the message by some factor delta, and you add some more noise E2. And then you define the ciphertext as E1 over F plus that noisy plaintext. And the difference between the two is that in this case, you need two polynomials to represent a ciphertext, and in this case, you just need one. And so when you see that, so you may say that, okay, so in this case, I just have one component to represent the ciphertext. So maybe that will be useful and can give rise to some speed up. Okay? So that idea has been put forward into work. So there is a work by Charlotte Bonte and other people. So the name of the cipher is known as final. So this one, yeah, sorry, maybe I was slightly too fast. So in the case of ring LWE, so typically we choose for the quotient polynomial x to the n plus 1, so a cyclotomic polynomial, so n to the power of 2. For NTRU, so there are two options. So the first one, again, is to choose that cyclotomic polynomial, so x to the n plus 1. But you could also choose x to the n minus 1 with n prime. So you have two options in this case. And so in those two works, so the first one is using so the cyclotomic polynomial, so x to the n plus 1. And so the second one, so when the scheme has been introduced, came into version. So the first one using x to the n minus 1 and a prime, and the other one so with the usual cyclotomic polynomial. And so the focus on this talk so will be so on the second scheme, so when using the quotient polynomial x to the n minus 1. So that version is no longer used, so it has been deprecated. So because, as you'll see, it's not longer, it's not secure. How it works? So this is a ciphertext. So this is an NTRU ciphertext. So as we just saw before. So F is the private key. E1, E2 are two error polynomials. F is a polynomial if you see small coefficients, so -1, 0, or 1. And so this is the delta, so Q over P. So I will just simplify a little bit the expression for the ciphertext. So I'll define E as E1 times E2 times F, and then we can write the ciphertext in this way, so E over F plus delta times M. Okay, so that's an NTRU ciphertext. So now if you define NTRU mod X to the N minus 1, so in this case, so if you need to decrypt, so first you compute the product of the ciphertext C and F, so this is the secret key. You get D, so which is equal to E plus delta M times F. Then you round, you reduce mod P, and you at the end so divide by F, and you get back the plaintext message M. Okay. To make that work, so the norm of the error should be smaller than delta over 2. Okay, just to be sure that there is not too much noise in the ciphertext. And so now I'd like to introduce that notion of what I call mildly noisy sample. So it's like this one, but you see that the condition now is stronger. So I assume that the noise is smaller than delta over 2 times square root of n. Okay. So those are ciphertexts with not too much noise. So you see that the difference is that factor here, so square root of n. So assume that I have such a plaintext, so which is mildly noisy, so with the error bounded like this. So what I can do, so of course, because x minus 1 divides x to the n minus 1, so I can reduce this relation mod x minus 1. And if you reduce mod x minus 1, so that's the same as evaluating at 1. So this is what you get. So I just multiply by f of 1, and this is what you have. Okay? So, I mean, when you look at that, so it looks like an LW encryption. You see, so you have the error, you have the scaling factor, and you have the message here. Okay? So everything here is mod Q. So maybe it will be easier to look at a picture. So this is the corresponding phase. So you see the error here, and you see in this case so m at 1 times f at 1. And if this is a valid LWE ciphertext, so it means that all those bits here should be clean. So it means that when the error here is positive, so it means that you have zeros, and when this one is negative, so you just have here a bunch of 1. Okay? And so, I mean, that's, again, very basic observation, but that allows you, I mean, it suggests an attack, and the attack is the following one. So what you can do, so remember that f has coefficient in minus 1, 0, and 1. So it means that the possible value for f of 1 at 1 is between minus n and n. Okay? So sign won't be able, I mean, you won't be able to detect the sign. So we just initialize, I mean, all the candidates for f1 as element in that set, so from 0 up to n. Then assume that you are given some mildly noisy ciphertext C. So it means that the ciphertext should be like this. And what you can do is that here, you can check that all those bits are clean. So in particular, it means that combination like 0, 1, and 1, 0 for those 2 bits here, it's not possible. Okay, because you should be only see zeros or 1. And so what you do, so you take a candidate for f at 1 here. Then you compute d at 1. So you have the ciphertext. You evaluate the ciphertext at 1. You multiply by your candidate f of 1. And you check if you have those 2 bits equal to 0 or those 2 bits equal to 1. Okay, you can take more. And if it is not the case, so you just disregard that candidate f at 1. And then you just iterate. And at the end, so if you just end up with one candidate, so it means that you find f evaluated at 1. Okay, so again, f is a secret key. So now let's apply that to the bootstrapping key that are used in NTRU. So in that case, the bootstrapping key are encryption, NTRU encryption of the LWE key bits, SI. And so if you look, so this is the error in a bootstrapped ciphertext. And so if you look at the variance of the error, so there is a term that is like this. And this is the value of rho. So you see that rho is proportional to n. So, and because you need to decrypt the ciphertext, so you have that condition to be satisfied. So square root of rho times the variance in the bootstrapping key should be smaller than delta over 2. And because rho is proportional to n, so it means that the ciphertext here are mildly noisy. All those bootstrapping key can be seen as mildly noisy ciphertext. And so it means then that you can recover them. And in this case, so you are just encrypting key bits. So I mean, it's enough to know the value using f evaluated at 1 to recover the key bits. Okay? So it means that if you are using for quotient polynomial x to the n minus 1, then you recover the key bits just from those bootstrapping keys here. And that's it. So I'll try to make a demo. I mean, that's something usually I don't do because of the demo effect. Let's try. Can you read? Yeah. So that's the main function here. So remember, so the goal was so you have your list, and then you just prune. So when the condition is not satisfied. So this is using parry. So this is f evaluated 1. And so no, so we are given some random mildly noisy ciphertext, and the goal is to recover back the value 69. Okay. So I have that function find key. So that's the list. I have no idea whether it works, so it should work. So you see that, okay. So in this case, so you see that there are still 86 possible candidates for f at 1. And so what we can do, so we can just add some more noise to the ciphertext, just to make that this distinction more discriminatory. So let's, no idea, so maybe that's too much. Okay, so oops, in this case it doesn't work. So I put too much noise. Too much. I told you that's the demo effect. Okay, so you found the key. So you see that in practice you don't need a lot of ciphertext. So in this case, just 3 was enough to recover the key. Okay, and that's it. So that's the end of the talk. Thank you.
Okay, thank you, Marc. Do we have any questions for Marc? Feel free to come to the front. If not, I can start with one. Marc, do you know of any other schemes that the attack could apply to?
So I mean, that of course does not apply to NTRU. I mean, because I mean the noise is larger in that case. So I mean, recommendation is to use the cyclotomic polynomial, I mean, for quotient polynomial. So,
okay, any other questions? Don't be shy.
Yeah, we do have time, so.
Hello, thanks for your talk. Just considering usual parameters to be secured, could we expect, using, for example, a lattice estimator or something like this, to find parameters with mildly noisy ciphertext which would seem secure with lattice estimator, for example? and which wouldn't effectively be secure
Okay,
to the
so
attack.
there is another condition if you are using NTRU, is that you should avoid to be in the what is known as the overstretch mode. So in practice, it means that you don't have all the freedom to choose the value of Q. So Q cannot be too large. So this is one of the reasons that you cannot choose a parameter as you would want to do. So
Thanks.
Okay, any more questions? If not, let's thank Marc again.
thank you.